Welcome back for another deep dive. This time, we're going to go really small, like subatomic small, to check out fermions.
Yeah, get ready because it's going to get kind of weird.
We'll be looking at some excerpts from a text all about the nature of these tiny particles, especially, um, especially this wild property they have called spin.
And who knows, maybe we'll get a glimpse of a new way to think about them using something called the resonance carrier ball.
Oh, yeah, that's a really interesting concept. But before we get ahead of ourselves, maybe how do we even know these particles exist? I mean, we can't even see them.
Yeah, it's true. Too small to see even with like the most powerful microscopes.
So how do we know?
It's all about the clues they leave behind, right?
Right.
So physicists, they use observations and experiments to find these clues, like unexpected blips or bumps or even stripes in their data. And that's how they figure out like space-time and fields and and particles.
Oh, okay. So it's kind of like detective work, looking for those tiny little hints.
Exactly. And as physicists found more and more of these clues, they started to realize that the universe is actually like jam-packed with all these different kinds of particles, like a whole subatomic zoo out there.
Whoa, a particle zoo. So
Yeah.
so okay, we've got this whole zoo of particles, but how do we make sense of it all? Do we just, I don't know, give them fun names and call it a day?
Well, the names are definitely interesting, but no, physicists like patterns, they like relationships, so they group these particles, into categories
Yeah.
based on their properties. And that's how we get these two main groups, fermions and bosons.
Okay, fermions, bosons. So are these like the two main branches of the particle family tree?
Yeah, you could think about it like that. So fermions are the particles that actually make up matter. So like you, me, the planets, stars, literally everything you can touch and see.
Fermions are the stuff.
Exactly, the stuff of the universe.
Okay, and what about bosons? What do they do?
They're the force carriers. They're the ones that are responsible for making all the fermions interact with each other. So they allow matter to interact, to form structures, to basically to do anything.
So fermions are the actors, and bosons are like the directors, making sure the whole show runs smoothly.
Haha. Yeah, that's a great way to think about it. And all of these particles and all of their interactions, we try to organize them using a framework called the Standard Model.
Okay, the standard model. So that's like the rule book for this particle universe.
Yeah, pretty much. Though some physicists think there might be more particles out there, ones we haven't discovered yet. So more chapters to add to the rule book.
Always a good sequel.
Yeah, right.
But let's get back to fermions and this crazy thing, this property called spin. You said it's not like a spinning top, so what is it?
Yeah, it's definitely one of those things that can make your head spin. It's what we call intrinsic angular momentum. So basically it's a fundamental property of all these particles.
Okay, you lost me at intrinsic angular momentum. What does that actually mean?
So in our everyday world, when something spins, right, we can see it rotate. But with fermions, it's not like that. It's more of a mathematical concept that helps us describe how these particles behave.
Okay, so it's a mathematical property, but it has real-world consequences.
Absolutely. In fact, the way that these fermions interact with magnetic fields is directly related to their spin. And the really weird part is how we actually measure this property.
All right, I'm ready for the weird part. Lay it on me.
So imagine you could grab onto a fermion, right, and physically rotate it. You would have to rotate it a full 720 degrees, so that's 2 complete turns, for it to return to its original state. Now, with normal objects, right, like in our everyday world, you only need a single 360-degree rotation.
Wait, seriously. So if I spin a fermion around once, it's not back where it started. How is that even possible?
It's one of those, mind-bending things about the quantum world. And we know this is true because of experiments like the Stern-Gerlach experiment back in 1922. They saw this 720-degree rotation behavior in silver atoms, which proved that spin was more than just a theory.
Wow. That's really, really counterintuitive. So spin is this mathematical concept, but it's also a real measurable thing that makes fermions behave in ways that we wouldn't expect, in our everyday lives. And you mentioned before that fermions are the stuff of the universe. Are there any like superstar fermions we should know about?
Well, the one you're probably most familiar with is the electron. It's one of the most fundamental and well-studied fermions, and it plays a huge role in our lives.
Oh, those little guys that power our world. What makes them so special? What makes electrons so special in the fermion family?
Well, they have mass, a negative charge, and of course they have that quirky spin we were just talking about. But they also follow something called Pauli's exclusion principle, which basically says that No two identical electrons can occupy the same quantum state. So think of it like each electron needs its own unique address in the quantum world.
Okay, so they're not big on sharing space, kind of like tiny territorial particles.
Exactly. And this principle it's super important for understanding how atoms are structured and why matter behaves the way it does.
Okay, yeah. Starting to see why electrons are such big players.
Hmm.
But even though we can describe their behavior with all this math, we still don't really get the why behind spin, do we? Like, what's actually going on that makes them need that extra 360-degree spin?
Yeah, that's the million-dollar question. It's one that's still like really stumping physicists. You know, the standard model, it's great at describing how particles behave, but it doesn't really get at the why.
A bit frustrating, isn't it?
Yeah.
But the source material we're looking at, it suggests that there might be a more intuitive way to think about fermions and spin. This thing called the resonance carrier ball.
Right. Now we're getting to some really interesting stuff.
So what is this resonance carrier ball, and how does it help us wrap our heads around spin?
Well, it's a model, a way to try to, visualize something that's really abstract, very mathematical.
Okay, I'm always up for a good visual.
Yeah.
So what does this ball actually, what does it look like, and how does it relate to spin?
Well, imagine a sphere. And inside the sphere, there's this incredibly complex, constantly moving belt. And this belt it's always twisting and turning, in a very specific way, almost like a three-dimensional Mobius strip.
Okay, so I'm picturing a tiny little subatomic contortionist, doing some crazy belt trick inside this ball. But how does this belt trick, how does it actually connect to this concept of spin?
Well, the idea is that this constant intricate motion of the belt, that's what actually creates the property that we call spin. So it's not a literal spinning in the way we normally think about it, but it creates that intrinsic angular momentum that defines a fermion.
So the belt trick is just a way to represent that momentum visually, even though we can't actually see what's happening inside the fermion.
Exactly. And remember how we were talking about how a fermion, it needs to rotate 720 degrees to get back to its original state? Well, the way that this belt, it twists and turns inside the ball, it reflects that same, strange property. It's called, get this, intercontinuous belt trick rotation.
Okay, so I'm trying to picture this belt constantly twisting and looping back on itself inside the ball. And it takes two full turns for that belt to get back to its starting configuration, just like it takes two turns for the fermion to get back to its original state. Am I getting that right?
Yes, you got it. So it's like the belt's motion is a visual metaphor for the fermion spin. And this model, it tries to go beyond, just saying spin is a mathematical property and offer a way to actually picture, what might be happening at a deeper level.
I appreciate any help I can get when it comes to picturing quantum mechanics, but I have to admit I'm still a bit skeptical. I mean, does this model actually give us any new insights, or is it just, a fancy way to describe something we already knew?
It's a great question, and honestly, it's one that physicists are still debating. The resonance carrier ball model is still fairly new, and it's definitely pushing the boundaries of how we think about these particles.
So it's more of a starting point for further exploration rather than a definitive answer.
Exactly. It's a way to, open up new avenues of thinking, to connect the kind of abstract math of the standard model to something a little more tangible.
And this brings us back to this mind-blowing idea you mentioned before, a two-layer reality. How does the resonance carrier ball model, how does it fit into that picture?
Ooh, this is where things get really interesting. So the text we're looking at, it suggests that this resonance carrier ball, with its complex internal dynamics, it might be showing us a glimpse into that deeper layer of reality, the layer of constantly changing space.
Wait, hold on. So you're saying that this belt trick that's happening inside this ball, it might not just be a metaphor. It might be an actual representation of what's happening at the most fundamental level.
It's a bold idea. It's definitely still speculative, but think about it. All our current models of physics, the standard model, they're all based on our observations of the universe, from our specific point of view. It's we're trying to understand how a giant complex machine works by only looking at its shadow.
So we're limited by our own perspective, by the tools we have to observe the universe.
Right, exactly. And this two-layer reality concept, it suggests that there might be a whole other level of reality, operating beneath the surface, a level that's way more dynamic and complex than anything we can, imagine right now.
So we have this this true reality, of constantly changing space that's hidden from us. And then we have the shadow reality, the one that, we experience and we try to explain with the standard model. And the resonance carrier ball, this is bridging the gap between the two.
That's the exciting possibility. Maybe by visualizing that motion inside the ball, we're actually getting, a little peek into the true nature of reality.
So these tiny little particles, these fermions, with their weird spin and this even weirder belt trick going on inside them, they might be holding the key to understanding the biggest mysteries of the universe.
That's a very cool idea, isn't it? And it really highlights how much we still don't know, how much is out there, left to be discovered.
Well, I'm definitely ready to explore. But before we, dive in any deeper, let's talk a bit more about how these fermions, these superstars, especially electrons, how do they actually affect our everyday lives? I mean, we know they're important for electricity, but can you give us some more concrete examples?
Right. For sure. Electrons they're everywhere in the modern world. Like every time you flip on a light switch, you're sending countless electrons flowing through wires, carrying energy, from the power plant to your house.
So we're literally harnessing these tiny particles to power our world.
Exactly. Or think about magnets, the way that magnets work. Those magnetic properties of materials, those come from the collective behavior of electrons and specifically their spins.
Okay, so behind the magic of magnets, what about that rule we talked about earlier, Pauli's exclusion principle, the one where two electrons can't be in the same state? How does that affect, things in the real world?
Well, that principle is actually the reason why matter takes up space, why it has that solidity. Imagine trying to cram all the electrons in your body into the same quantum state. It'd be like trying to fit, 1,000 people into a phone booth. Impossible.
So thanks to the rules of quantum mechanics, I get to have a physical form. I get to enjoy all the benefits of not being squished into a subatomic singularity.
That's right. And that's really just scratching the surface when it comes to the impact of fermions, and their quantum weirdness on our everyday lives.
Okay, my brain is officially full. We've covered so much from, this particle zoo to the 720-degree spin, this resonance carrier ball, this two-layer reality. Where do we even go from here?
Well, I think it's a good time to pause here, give our listener, time to process all this. We'll be back soon for the final part of our Fermion adventure.
Great idea. Until then, stay curious and open to the wonders of the subatomic world. Welcome back to the final part of our deep dives into the world of fermions.
It's been quite a journey, down to the subatomic level.
My mind is still kind of stuck on that whole two-layer reality thing. It's like, we're watching this cosmic movie, but we're only seeing the trailers, not the full mind-blowing epic.
Makes you wonder what's really, going on behind the scenes, what secrets the universe is still hiding.
Exactly. And you were saying before that fermions, especially those electrons, those little guys might hold the key to unlocking some of these secrets. How do we even start to follow their lead?
Well, remember that model we talked about, the resonance carrier ball? With its intercontinuous belt trick rotation. Maybe that's a good place to start.
Right, the cosmic contortionist. But how do we go from a visual model to actually understanding this deeper layer of reality? It seems like a big leap.
It is a big leap. And it's going to take, some serious ingenuity, creativity, and maybe even a bit of, scientific daring.
So we got to think outside the ball, so to speak.
Exactly. We need to be willing to challenge our assumptions, explore new ways of thinking about space and time and what reality even is.
It's like we're, those early explorers setting out into uncharted territory with just our curiosity and a bit of skepticism.
I like that analogy because just like those explorers, I think we're bound to run into, unexpected challenges and some pretty breathtaking discoveries, along the way.
Speaking of discoveries, the text mentions that, further research into this model, into the resonance carrier ball, it could lead to some pretty revolutionary insights. What kind of, breakthroughs are we talking about?
Well, I mean, for starters, we might finally crack the code on spin, really understand like why fermions behave the way they do, why they need that extra 360-degree rotation, to get back to their starting point.
And that would be huge, right? I mean, it would
Yeah.
be like filling in this major gap in our understanding of, particle physics.
Oh, absolutely. But it goes even deeper than that. Remember that two-layer reality. If this model, if it really is giving us this little glimpse into that deeper layer, the constantly changing space, well, then understanding its secrets could lead to a totally new understanding of space and time, how they interact, how they create the universe we see.
Whoa, okay. So we're not just talking about revising the standard model, we're talking about like rewriting our whole understanding of how the universe works.
It's a mind-blowing possibility, right? And
Yeah.
it has the potential to revolutionize, not just physics, but our entire worldview.
I'm getting chills just thinking about it. But let's be realistic here.
Mhm.
What are the odds that this one model, this resonance carrier ball, actually holds the key to, to all these profound insights?
Well, I think that's the beauty of science, right? We can't know for sure until we go out there and explore, until we push those boundaries and see what we find.
So even if this particular model, doesn't lead to the breakthroughs that we're hoping for, the process itself of exploring it, of asking those questions, it's still valuable.
Oh, absolutely. Every new idea, every experiment, every model, it's a step forward, in our quest to understand the universe. And sometimes those steps, they lead us down these unexpected paths to discoveries that we never could have imagined.
Like we're on this grand adventure, and every twist and turn is, leading us closer to something amazing.
I couldn't have said it better myself.
So as we wrap up this deep dive into the world of fermions, what's the one thing, the one big takeaway you want our listener to walk away with?
I think the most important thing is just to remember that the universe it's full of mysteries, and that's a good thing. It means
Yes.
there's always more to learn, more to explore, more to discover.
And who knows, maybe someday one of our listeners will be the one to, unlock the next big secret of the universe, inspired by these amazing little fermions.
I wouldn't be surprised at all.
Well, thanks for joining us on this incredible journey. It's been great to explore with you.
The pleasure was all mine. Until next time, keep those minds curious. Stay open to the wonders of the universe.
And remember, never underestimate the power of a tiny particle, especially one that can spin in 2 dimensions at once.
Indeed.
This has been The Deep Dive. See you next time for another plunge into the depths of knowledge.